let me shut up and introduce, hand over to Jinder, who is going to introduce our speaker today, Nicole Fury. If I could just say, of course, almost the principal reason we're here and that this entire seminar series is taking place is because it has been inspired to a great extent by the program with which Nicole is herself so now closely identified. So I'm going to hand over to Jinder, who will have quite a bit more to say.
Thank you, Michael. I couldn't agree with you more about what you said just now about Cole. So it's my pleasure to welcome Cole Fury to give today's lecture on octonions and particle physics. Cole obtained her PhD from Perimeter in 2015, and her thesis titled Standard Model Physics from an Algebra is one of the best-known PhD theses in high-energy theoretical physics in recent times. This thesis left a mark on studies of octonions in particle physics to the extent that her name has almost become synonymous with the subject. Her 14-part set of video lectures on division algebras and the standard model is a must-see for anyone interested in getting into the subject. For me, her most significant work is charge quantization from a number operator, where the properties of one generation of standard model fermions are convincingly derived from a Clifford algebra motivated from the complex octonions. I also have an interesting personal story to tell. I first heard of octonions only 3 years back when my own work indicated that 8-dimensional spaces could be significant for unification. However, I had never heard of such a space, so I Googled the term 8-dimensional spaces. Google returned a Quantum magazine article on Cole and her work on the octonions, and within minutes of reading it, I knew this to be what I was looking for. That same evening, I wrote to her, and she was kind enough to immediately send back an encouraging reply. Since then, it has been octonions all the way, and none of it would have been possible without the groundwork done by her. So thank you, Cole, and over to you for this exciting lecture.
Thank you so much to Jinder. That was extremely kind. Thank you. Okay, so first of all, I want to say thank you sincerely to both to Jinder and to Michael for organizing this lecture series. These things, of course, take a lot of work, and I hope that you know that many of us are really grateful to you for putting it together. The atmosphere so far has been really positive, and many of us really appreciate that. And before I start, I would like to mention that many of the results I'm going to be discussing today were done in collaboration with 2 people, namely Beth Romano, who is a number theorist at King's College London, and for earlier work, Mia Hughes, who completed her PhD on supergravity at Imperial College London. Now, in this talk, I'm going to be discussing some work on 3 generations, especially later on in the talk. And we're, of course, not the only ones to be working on this problem. There's, of course, Corinne Minogue, Tavian Dre, and Robert Wilson, who have an E8 3-generation model. There's David Chester, Mike Rios, and collaborators who've been working on 3-generation E8 models. Niels Gresnik and Adam Gillard, who've worked on 3 generations and complex CL8. Tejinder Singh and his group, who have worked on E8 and the exceptional Jordan algebra, Ivan Todorov, Michel Dubois-Violette, who've worked on the exceptional Jordan algebra, Latham Boyle, who's worked on the exceptional Jordan algebra, David Jackson, who I believe has also worked with 3 generations in the exceptional Jordan algebra. And now that I've got this list down, I think also Greg Trailing, I should have also included. And I'm certainly forgetting people on this list unintentionally. But the point is that there's quite a number of us now that are working on this, this challenge. Okay. So with this said, as theorists, every once in a while, it's good to take a step back and ask, what is my best guess to the following question? That is, what is the universe made of and how does it work? What is my best guess? That is, imagine that tomorrow that our game of building theories would for some reason be over. Or imagine that our profession were soon to be overtaken by some accelerating, self-improving artificial intelligence. If you were asked to lay your cards on the table, what would your best guess be? Well, this is, of course, a difficult question to answer since we're always working with incomplete information. Nonetheless, in this talk, I would like to offer for you what is my current best guess. And I'm going to run you through the logic right from the very beginning. So every research project starts out with some sort of intuition or some picture of what nature is at its essence. For example, in quantum field theory, we have a picture of particles on a spacetime where the particles are described by excitations of a field living on a manifold. Physical theories, of course, begin with some initial input or some initial structures that are meant to make up reality. Of course, these structures should be chosen very carefully, seeing as how one wrong assumption may lead your theory to shipwreck. That is, every extra structure carries with it a risk of being wrong. Now, our current best model of particle physics is known as the Standard Model. On one hand, the Standard Model works better than any previous particle model that we've had in making predictions in particle physics. On the other hand, it leaves many basic questions unanswered. For example, why is it rooted in the gauge group SU3 cross SU2 cross U1 over Z6 and not some other group? Why do we have the spacetime symmetries that we do? And even if we were to understand where these symmetries came from, we would still be unable to explain why the Standard Model has this long and apparently senseless list of fundamental particles. Furthermore, it doesn't answer what makes up dark matter, dark energy, believed to comprise 95% of the mass energy content of the universe. And this isn't even an exhaustive list of open questions. So one might wonder if perhaps we have been making some assumptions, or there have been some assumptions made in our construction of the Standard Model that could be preventing it from accessing a more complete description of nature. Now, as you know, the Standard Model has quite a lengthy list of initial inputs. We begin with the 3+1 dimensional spacetime manifold. A manifold in and of itself has non-trivial structure. We then add in a Fock space, matter fields, gauge fields, Higgs fields. We impose the quantization procedure, etc. Now, given that every extra structure brings with it a risk of being wrong, we might instead opt to minimize our initial inputs. That is, we will seek to minimize our initial inputs for practical reasons, because this is the most cautious way to proceed. Now, another reason that we might consider aiming for a minimalistic theory is for reasons of beauty. So it's my personal opinion that mathematical elegance is a valid guide in model building. But the question is then, well, who gets to decide what elegance is? My personal take is that a more beautiful theory is one that compresses the physical data more efficiently. So in the case of the Standard Model, we have described aspects of a very complex natural world by using a very complex theory. And what would be more beautiful in my mind is a minimalistic set of initial inputs that could still output the same predictions. So we could take the game of Go as an analogy. Go has a set of rules that are simple enough to teach a child, but the resulting scenarios are complex enough that adults can spend their lives studying them. Now, building a successful minimalistic model presents for us a bigger challenge for a couple of reasons. The first reason is that your theory now has a lot more work to do in terms of creating something complex out of something simple. It's also more challenging for sociological reasons. That is, nobody's colleagues are impressed by simple machines. So at the end of my undergrad and throughout my master's, I began playing a bit of a game. Now, here's the game. The game is to answer what could be the smallest set of initial inputs to start with, whereby you still capture as many known features of nature as possible. For example, you might want to capture the irreversibility of time, or the existence of matter and its interactions, or the existence or emergence of spacetime, the 3+1 dimensionality of spacetime, quantum non-locality, or entropy increase, etc. So a big dream would be something along the lines of starting with some minimal inputs and arriving at, say, standard model scattering amplitudes. As a side note, I want to point out that we physicists often make the mistake that mathematicians know not to make. That is, once we have one established theory that can make predictions, like the standard model in the form of a QFT, we often assume that it is unique, that it's the only story that is going to produce for us the answers that we need. Or in other words, we conflate existence with uniqueness. The standard model is a machine that, amongst other things, spits out probabilities. A probability is just a real number between 0 and 1. There could conceivably exist a much simpler model that could spit out the same probabilities. Now, as a first attempt at this problem, I wanted to aim for something that does away with the hierarchical system that we assume in QFT, that is where we have various fields living on top of a space-time manifold. So one picture that I proposed along these lines is based solely on directed graphs. So clearly this resembles Feynman graphs, except for the fact that it is not embedded in a separate background space-time. Instead, these directed graphs would be the only objects in the model. So everything that we perceive as matter, its interactions, the apparent space-time in which it would live would ultimately have to come from only these directed graphs. This was an idea that I proposed in my Part 3 research essay in 2006. Later, I included it in the first chapter of my PhD thesis. At the time, I received a significant amount of pushback for this idea. There was a very small number of us at the time that quite literally risked our careers in order to put these ideas forward. One example I'm aware of comes from Fotini Marco Polo and David Cribbs, who suggested that the world should be constructed using quantum information processing systems, again, with no notion of a separate underlying spacetime. In more recent times, these sorts of ideas have gained mainstream acceptance, with similar standalone graph models being proposed by established professors. So this was the first round of this minimalistic model building game. However, you can see that we already run into a problem, which incidentally the standard model also faces. That is, as with the standard model, there's no obvious explanation as to why spacetime appears to be 3 + 1 dimensional. So how might we face up to this problem? So this is where we might very cautiously add in more structure. Namely, we're going to add in the structure of an algebra. And the idea is that if these directed graphs were in fact representing the operations of an algebra, then maybe we could use the properties of this algebra in order to give the dimension of what we eventually see as an emergent spacetime. Okay, well then which algebra do you choose? As a first example, you could consider the algebra of the quaternions, which has this, because it's got this suggestive structure, it's got 1 real dimension and 3 imaginary dimensions. Now, as I mentioned early on in my Part 3 essay, the basic notion would then be of graphs of quaternionic triads, like quaternionic vielbeins, branching out over and over and over again, and sometimes also doing the reverse process, where they join edges together at a vertex. Now, this branching is supposed to give general phenomena, such as things like entropy increase and the universe's expansion. And joining of edges at a vertex, on the other hand, is meant to ultimately give us phenomena such as gravity, interactions in what we eventually might come to know as measurement. And now notice that these quaternionic triads bear a striking resemblance to the vielbeins of general relativity. And we're going to get back to this later. Now, any physicist who has worked with the quaternions know that they almost give you the physics that you want, but not quite. That is, the inner automorphisms of the quaternions give us SO3, not the Lorentz group. But it turns out that if you tweak this slightly, then several doors open up. That is, in physics, we've got these familiar 2x2 Hermitian matrices known as the Pauli matrices. And there's this well-known correspondence between sigma x and I sigma epsilon 1, sigma y and I epsilon 2, sigma z and I epsilon 3, where I is the complex imaginary unit and epsilon 1, 2, 3 are quaternionic imaginary units. Now, furthermore, it's a well-known fact that there is an isomorphism between the 2x2 complex matrices and the quaternions, now with complex coefficients. So not only can we get these physically relevant Pauli matrices from the complex quaternions, but we can furthermore get the Lorentz group. That is, the group of inner automorphisms of the complex quaternions is given by none other than SO31. Now, it turns out that there's this old paper from the 1930s by A.W. Conway, which shows that you can describe Dirac spinors, 4 vectors, the field strength tensor, using nothing more than the complex quaternions. As you may recognize, this is already most of the Lorentz representations that we use today in the Standard Model. Okay, so this is hopeful. And what I want to show you now, number one, is that there is in fact a bigger picture behind Conway's findings having to do with discrete symmetries. This bigger picture will allow us to get a complete set of the Standard Model's representations. This involves the inclusion of scalars and the selection of Majorana's spinor representations over Dirac. And finally, this bigger picture will lead us to an idea that might help us address the following question. That is, if all we have is this algebra, these algebraic graphs, then how are things like field strength tensors and spinors supposed to pop out or emerge? So let's talk about this last point first. So if all we have is an algebra, then how are things like field strength tensors and spinors supposed to pop out? Now, a bigger picture behind Conway's findings that I was referring to refers to the idea of an ideal. So let's say we have some algebra, in this case given by the complex quaternions. Then a left ideal is a special subalgebra whereby if you were to left multiply any element A in the algebra onto an element V in the ideal, then their product, V prime, will always get pulled back inside the ideal. So loosely speaking, you can think of ideals as an algebra's version of a black hole, in that it will pull any element into itself via multiplication. So these ideals, you can think of them as the stable subspaces of the algebra. So now what we're going to find shortly is that each of the Lorentz representations of the Standard Model can be identified as objects that generalize the notion of an ideal. So in this sense, the scalars, the spinors, the 4 vectors, the field strength tensor can be seen to be stable subspaces of the algebra. For mathematicians, these are known as invariant subspaces under some action of the algebra on itself. So the idea I propose in my thesis is very much in the flavor of Darwin's mechanism of survival of the fittest. The fact that ideals are stable under multiplication could be viewed as them surviving over time. Now you notice that in this example, we assumed that the multiplication rule is left multiplication, but we could just as well have assumed right multiplication or perhaps something more general, such as an adjoint action. So what I'm about to show you is that the scalars, spinors, 4 vectors, and field strength tensor, the various Lorentz representations of the Standard Model, can each be thought of as generalizations of ideals under different multiplication rules. A more precise way to say this is that each of the Lorentz representations of the Standard Model can be shown to be invariant subspaces of the complex quaternions under some action of the algebra on itself. So this next part is important. Okay, the next part is important because we're going to use some of the details in the later parts of the talk. Okay, so the complex quaternions have these 3 discrete symmetries. We've got the complex conjugate, which maps complex I to minus I. We've got the quaternionic conjugate, which takes quaternionic epsilon 1, 2, and 3 to minus epsilon 1, 2, and 3, and it also reverses the order of multiplication. And finally, we've got what we call the Hermitian conjugate, which does both the complex conjugate and the quaternionic conjugate at the same time. Now, under each of these discrete symmetries, the complex quaternions split into two pieces. For example, starting on the left-hand side, we get one piece, which is invariant under the complex conjugate, and the other piece picks up a negative sign under the complex conjugate. And the same goes for the Hermitian conjugate. One piece is going to be Hermitian, and the other one's going to be anti-Hermitian. And the same is true for the quaternionic conjugate. There's one piece that picks up a plus sign, and the other one picks up a minus sign. Now, based on these discrete symmetries, we can now define actions of the algebra on itself, or in other words, generalized multiplication rules. So these actions are chosen so that, for example, an object that starts out Hermitian will continue to be Hermitian no matter which A in the algebra that you apply to it. And the same goes for the anti-Hermitian piece. So any A that you apply onto it, if it starts out anti-Hermitian, it will end up anti-Hermitian again. So this is the multiplication rule, or more precisely, the action that we use for the Hermitian conjugate. And then there's also a similar action for the quaternionic conjugate that looks like this. You'll notice that the two, they look similar to each other. It's because the Hermitian conjugate and the quaternionic conjugate are both anti-automorphisms. Now for the complex conjugate, on the other hand, here's what the action looks like. The P here is nothing more than a chirality projector. So under each of these actions, every one of these subspaces listed here is stable. Now, finally, we need to identify what these stable subspaces are going to represent for us. You can probably already guess. Now, suppose we take some element A to be an element of the group SL2C, written, of course, in the language of complex quaternions. Then based on the specific way that these subspaces transform, these two subspaces on the left-hand side can each be identified as a Majorana spinor. The two subspaces in the center can each be identified as 4 vectors. And the two subspaces on the right-hand side can be identified as a complex scalar and a 6 real dimensional field string tensor. So finally, there is another feature that is going to come up again later, and that's that in the case of these two anti-automorphisms, C cross H gets broken down into a Jordan algebra and a Lie algebra. So here the Hermitian subspace gives a Jordan algebra, and the anti-Hermitian subspace gives a Lie algebra. And the same goes for the quaternionic conjugate. Here the scalar gives a Jordan algebra, and the field string tensor gives a Lie algebra. Okay, so let's take stock now where we've come so far with this model. So we started out with the minimalistic input that nature is made of nothing more than directed graphs. Then we noticed that a generic directed graph is not going to lead to the emergence of a 3+1 dimensional spacetime. So from here, we propose considering that these directed graphs represent the operations of an algebra. Now, which algebra should we choose? We found that the algebra of the complex quaternions can give us quite a bit of mileage. That is, we found that the discrete symmetries of the complex quaternions provide us with an exquisitely compressed way to describe scalar spinors 4 vectors in the field string tensor. And this gives us the complete set of Lorentz representations that we use in the standard model. Now, I want to emphasize that the system of Lorentz representations is in many ways the poster child for what a minimalistic model should look like. What we're going to do for the rest of this talk is demonstrate a way to take this system and to scale it up. Okay, so how are we going to do this? Well, the particles of the standard model have more properties beyond just their behavior under Lorentz transformations. They, of course, have color, weak isospin, weak hypercharge, for example. So is there a way that we could also model these extra degrees of freedom? Well, let's take a closer look at this algebra that we're using. The complex quaternions are given by C cross H, where the tensor product is over R. And it's straightforward to see that this C cross H is trivially equal to R cross C cross H, where the R is the real numbers. And at this point, you might also notice that this algebra is the tensor product of 3 out of 4 of the finite dimensional norm division algebras over R. So it's then natural to wonder, well, what if we were to include the final norm division algebra, the octonions? Could the combined algebra, RCHO, then allow us to include the remaining internal degrees of freedom? Well, this question becomes even more unavoidable when you notice that the number of internal states in one generation adds up to 8. That is a neutrino, red, green, and blue down type quarks, red, green, and blue up type quarks, and a charged lepton. Now, there are examples of earlier researchers who have noticed similar patterns. Namely, in the 1970s, Gunaydin and Gursey identified a quark-antiquark pair under SU3 within the octonions. And as for the full RCHO algebra back in the 1990s, Jeffrey Dixson proposed a series of particle models based on the algebra of 2x2 matrices over RCHO. RCHO makes up the components of this algebra, so it's why we often refer to RCHO as the Dixon algebra. Jeffrey is the first person I know to have had an algebra named after him. Now, I should point out that Murat Günaydin as a student, Jeffrey Dixon, and a number of us attending this conference have had to weather a lot of pushback for coming forward with these ideas on the octonions. Well, this for me is a really curious state of affairs. The octonions are just a mathematical object, just like any other object, just like any other mathematical object. So having a prejudice against the octonions makes about as much sense to me as having a prejudice against the number 7. A recurring theme in my talk will be recurring themes. So since we're here, why don't we linger on this point a little? On a somewhat related note, I want to mention that over recent years, there have been more established physicists working on the octonions than there were before. So to these mathematical physicists, I would like to say, welcome. It's nice to have you here. Secondly, to these established professors, I would also like to remind you that there have been many researchers working on octonions long before you got here. Many of those researchers who are here tonight, or who might be listening to this later, risked their careers in order to work on this topic. Some of them have even been unable to continue in academia because of that choice. So with this said, I would like to encourage you to be as inclusive as possible with these researchers when you write your papers and you tell your story. This goes especially in the case where you've made use of the work of these earlier researchers, because many of these physicists have taken a risk and have paid a price that you have not. Okay. So we're now at the point where we have now upgraded our algebra to RCHO, a 32 complex dimensional algebra, and we would like to eventually calculate standard model scattering amplitudes. So our first step then is to try to model the full particle content of the standard model, much in the way that we modeled Lorentz scalars, spinors, 4 vectors, and the field string tensor using the complex quaternions. Okay, so what's the standard model's particle content? Well, as you know, the standard model's gauge group is SU3 cross SU2 cross U1 over Z6. And under this group, the standard model has this very long and seemingly arbitrary list of irreducible representations. The first entry here in the brackets refers to the irrep under SU3 color. The second refers to the irrep under SU2 left. And the third refers to weak hypercharge. And the subscript at the end refers to the multiplicity of these off-shell states. Now, if we add up all the degrees of freedom in this list, taking every particle as off-shell, counting the Higgs as its own independent space, and finally including an additional set of 3 sterile neutrinos, then we have 244 real degrees of freedom in total. So roughly 250, which is quite a lot. Well, let's check back at this RCHO algebra that we're interested in. How big is it? It's 64 real dimensions. So it seems like we might be stuck. How are we going to model roughly 250 real degrees of real off-shell degrees of freedom of the standard model when all that we have to work with is a 64 real dimensional algebra? Well, one idea is to take a hint from nature. Nature succeeds in describing the entire human genome using only 4 bases, A, C, T, and G. Well, how does it accomplish this? Nature accomplishes this not by considering those 4 bases alone, but instead by considering sequences of the bases. So let's see what would happen if we were to consider sequences of RCHO elements, one being multiplied onto another. Might we be able to describe the fermions and bosons of the standard model inside these sequences? Now, sequentially multiplying RCHO elements onto RCHO elements generates something familiar to mathematicians known as its multiplication algebra. You can think of RCHO's full multiplication algebra as being isomorphic as a matrix algebra to the 32 by 32 complex matrices or to the complex Clifford algebra CL10. It's generated by using 10 objects, which we're going to call gamma J. And you can think of these 10 gammas as being like the 4 A, C, T, and G bases of genetic sequences. So these 10 gammas generate the complex Clifford algebra CL10. So this is CL10, but CL10 with a lot of extra structure due to the fact that it's generated by RCHNO. And this extra structure will then give us a number of ways that we can break CL10 up. Okay, so we're considering these sequences of RCHO elements, and it generates the CL10, but it's not just CL10, it's CL10 with extra structure, and we're going to use this extra division algebraic substructure to break CL10 up. Now, it turns out that we can write RCHO's full multiplication algebra as a factorization that is interesting on mathematical grounds. That is, we can split up complex CL10 as the real CL08, familiar from the Bott periodicity on real Clifford algebras, and complex CL2, familiar from Bott periodicity of complex Clifford algebras. This might relate to what John Bias and others call the tenfold way. As a physical interpretation, I would like to identify the standard model's off-shell states with CL08. And then there's going to be this CL2 factor that's left over. Now, given the isomorphism between complex CL2 and the real CL30, we might be able to adopt an interpretation of this CL30 part that so that the CL30 part represents the rudimentary algebraic beginnings of a three-dimensional space, that is 3 legs of some evolving triad. From here, we might try to incorporate gravity. So in geometric terms, the setup could give us the algebraic beginnings of an emergent 11-dimensional space where we find ourselves with a 3-dimensional spatial base manifold and a fiber producing standard model degrees of freedom. Now, CL08 in and of itself is an algebra worth paying attention to for a number of reasons. Number one, it is roughly the right number of degrees of freedom of the standard model's off-shell states. So CL08, we're looking for about 250 real degrees of freedom, and CL08 is 256 real. Number two, in the world of real Clifford algebras, CL08 is essentially unavoidable. Well, what do I mean by unavoidable? So let's say that you were to consider the space of all real Clifford algebras in the form of CLST. Here, the S and the T can be any integers greater than or equal to 0. So there's an infinite number of these Clifford algebras. Then Bott periodicity tells us that if you were to choose one of these CLSTs at random out of this infinite set, then with overwhelming probability, the Clifford algebra will be of this form. That is CLS0T0 cross CL8 cross CL8 cross CL8 cross CL8 over and over again, where the S0 and T0 live within 0 to 7 inclusive. So in other words, it will have this little end piece, C0, CL, S0, T0, followed by this long string of CL8 cross CL8 cross CL8, CL8, and so on. So it's going to be overwhelmingly dominated by factors of CL8. So it's in this sense that I mean to say that CL8 is unavoidable. So this touches on a point that I'd like to make about which mathematical structures we choose when we're building physical theories. That is, when a theorist is building a physical model, they could choose the prince of mathematical structures. That is, they could look for a mathematical structure that is somehow the most distinguished or the most special. Or alternatively, we might opt instead for a mathematical structure that is the most common. CL8 is an example of a mathematical structure that is the most common, at least within the space of real Clifford algebras. So we could say that CL8 is special because it is not special. Now, a third reason why I find CL08 interesting is because it looks, loosely speaking, like it might give us a natural incarnation of a Fock space. So let's say we can indeed describe a state in the standard model as an element of CL08. And this is what we're going to argue shortly. Then this would count as a one-particle state. And let's say now that we were to take some Clifford algebra, CLST, at random. Then an element in this space might be viewed as a multi-particle state. And here the number of particles in the multi-particle state would correspond to the number of factors of CL08 that the Clifford algebra has. Then finally, taking superpositions over different size Clifford algebras could give us something along the lines of a Bott periodic Fock space. We'll start with a 0-particle state, then we add in a 1-particle state, the 2-particle state, and so on. We might even include the totality of all real Clifford algebras by summing over all possible S and T's. Now, as a final note, I should mention that it may be useful at some point to also consider graded tensor products, in that these might help us tease out fermionic and bosonic behavior. So to the best of my knowledge, this idea of a Bott periodic Fock space was first introduced here. Okay, so let's retrace our trajectory. We started out by arguing that the safest possible theory is one that makes the fewest number of assumptions possible. We then proposed one such model built from only directed algebraic graphs. That is, we do away with any additional notion of an underlying spacetime. Now, when that algebra is chosen to be the complex quaternions, then we find that we can describe all of the Lorentz representations of the standard model in a concise way. Well, these Lorentz representations are defined by their behavior under discrete symmetries. And now we want to scale this up. So when counting all of the off-shell degrees of freedom in the standard model, we find that we need a space that is roughly 250 real degrees of freedom. As it turns out, we find a relevant 256 real dimensional space by taking a certain real slice of RCHO's multiplication algebra. This CL08 slice is especially interesting for us because it is ubiquitous in the world of real algebras. Furthermore, it might just supply us with a natural incarnation of a Fock space. So now we're at the point of describing how standard model degrees of freedom can be embedded inside of this CL08. So for practical reasons, we're going to do this by first analyzing its structure at the complexified CL8 level, and then we're going to restrict down to the real slice. Now, it's crucial to note that we're not dealing simply with CL8, but rather CL8 generated by the division algebras RCH and O. So we're in fact going to have a lot of additional substructure here within these algebras, and this is what's going to help us break the algebra down. So in our first step, we're going to bring to light some important substructure that comes about from the octonions. So as many people here will know, the left multiplication algebra of the octonions is given by CL06. And furthermore, you may know that it is possible to describe the volume element of this Clifford algebra as a single octonionic imaginary unit. So for concreteness, we're going to call this imaginary unit E7. But of course, there's an entire 6 sphere of candidates that we could choose for this imaginary unit. So this octonionic substructure is going to single out for us a volume element expressed in terms of an octonionic imaginary unit. Now, with this octonionic imaginary unit E7, we can construct projection operators, which we're going to call little s and little s star. Now, these projection operators may be viewed as generalizations of a chirality projector that's familiar to you from the Dirac algebra. Now, the octonions have this peculiar property that any octonion multiplying from the right can always be rewritten as chains of octonions multiplying from the left. And so this means that the same octonionic imaginary unit, E7, will give us a second pair of projection operators, namely which we're going to call capital S and capital S star. So here the capital R here refers to right multiplication. So this octonionic substructure of our complex CL8 is going to give us two sets of commuting projection operators. And so the question is now, well, what are these octonionic projectors going to do for us? Well, they're going to take our complex CL8 and they're going to partition it into blocks. Now, there's one curious feature about these blocks. You'll notice that these blocks are of various different sizes. The thing that's curious is that these sizes happen to fit the standard model's particle representations rather closely. Incidentally, this partitioning is an example of what's known as a purse decomposition, and is discussed in detail towards the end of this talk, linked here. The purse idempotents correspond to projective measurements in quantum theory. So here is the particle content from the standard model that we would like to describe on the left. And it might seem like a small miracle if these representations on the left were to fit tightly into the blocks on the right-hand side. After all, these blocks sprang up from just a single octonionic imaginary unit. So you might actually appreciate that we're actually asking for three small miracles. First of all, that the division algebras, this division algebraic substructure of our CL8 is going to somehow single out the symmetries that we see in particle physics. Secondly, we need these particle representations to fit tightly into the blocks. And finally, you may notice that there are 23 irreducible representations here on the left-hand side. And it would not be very convincing if each of their transformation rules needed to be specified individually, as we do in the standard model. Instead, what would be much more convincing is if we had a relatively simple transformation rule that describes how each of these representations transform. That's our wish list, and let's see how far we get. So let's start by seeing how this octonionic substructure might single out some symmetries for us. Now, a natural expectation is that our symmetries are going to respect these octonionic projection operators. So we expect that the symmetries are going to commute with the projectors. This then restricts the symmetry generators and our eventual covariant derivatives to live in the diagonal blocks. Now let's consider a linearization of the Hermitian action familiar from the beginning of this talk. So just as we had earlier in the C cross H algebra, we find that the block splits into two parts, one being where did this go? It's going to split into two parts. One part is going to be anti-Hermitian and we'll give a Lie algebra. And the other part is going to be Hermitian and it's going to give a Jordan algebra. So this means that each of these blocks is going to be partitioned into a Lie algebra and a Jordan algebra. Now, the elements in the diagonals should correspond to a covariant derivative in our model once. Oh, first I need to say, so these now these Lie algebras that we just described will give us a set of symmetries that we can consider. So the Lie algebras that we find in these blocks are 4 real dimensional, 36 real dimensional, 36 real dimensional again, and 4 real dimensional. And the Jordan algebras in these blocks are going to be the same size as those Lie algebras. Okay. So now the elements in the diagonals should correspond to a covariant derivative in our model once a real slice is taken and once it's made into a gauge theory. So that is the pieces that correspond physically to momentum operators, and the pieces that we have pieces that correspond to off-shell gauge bosons, including their polarizations. We furthermore notice that the color and generation parts of these Lie algebras are described by the octonions, while helicity and isospin are described by the quaternions. Now, these Lie algebras and Jordan algebras are physically significant because of their expected correspondence to this covariant derivative, but they do not match the symmetries of the standard model gauge group. So you can see that we have too many symmetries here. In fact, some of them may be viewed as symmetries that rotate octonions into quaternions and quaternions into octonions within these blocks. But we would like our symmetries to respect this division algebraic substructure, so let us restrict ourselves down to the Lie subalgebra. Lie subalgebra that forbids these transitions between quaternions and octonions. When we do this, we find that we get two copies of SU3 plus U2 plus U2. Now note that this result comes from the complex CL8 case. When we take the real slice, and we're going to lose half of our degrees of freedom. Now, you may have noticed that there's a kind of mirror pairing between the algebras, where there's this reflection symmetry that occurs across this purple axis. So this leads to something that we're going to call multiplet mirroring. In the complexified case, for every symmetry element on one side of this mirror, there's going to be another independent symmetry on the other side. Furthermore, we expect that when these blocks are applied to the fermion off diagonals, one set is going to act on the left-hand side, and the other one is going to act on the right-hand side of the fermion. Well, what does this multiplet mirroring, what is it going to mean physically? Well, physically, we find that the octonionic SU3 symmetries, when they act on one side of a fermion, they mix possible color degrees of freedom. And when the mirror set of octonionic SU3 symmetries act on the other side, then they mix possible generations. Similarly, we find that when certain quaternionic SU2 symmetries act on one side of a fermion, then they mix possible quark helicities. And when the mirror set of quaternionic SU2 symmetries act from the other side, then they mix possible isospin states on left-handed particles. Finally, we find that, that when the other set of quaternionic SU2 symmetries act on one side of a fermion, then they mix possible lepton helicities. And when the analog set of quaternionic SU2 symmetries act on the right-hand side, then they mix possible isospin states of right-handed particles. So these are the various symmetries that we get in the full complexified CL8. Now the question, and so algebraically, you can see that they come in these pairs. So this is what we found for the complex CL8 case. And so the question is now, well, what happens when we restrict down to CL08? Well, when we restrict down to CL08, we shave off half the degrees of freedom. In the process, we lose half of our Lie algebras and half of our Jordan algebras on the diagonals. In other words, we now have only an SU3 plus U2 plus another U2 algebra, Lie algebra, and then we've got another Jordan algebra that's analogous to those. So one way to interpret this situation is to look at these 6 types of transformation and to characterize half of them as Lie algebraic and the other as Jordan algebraic. Well, how are we going to identify which correspond to Lie algebras and which correspond to Jordan algebras? One obvious identification is to notice that half of these transformations describe internal symmetries. So namely SU3 color, SU2 left, and SU2 right. So we might identify these with Lie algebras. And the other transformations describe mass and spin. So we might identify these as Jordan algebraic. So to address this final item in our wish list, the octonionic substructure of our CL8 does supply us with a natural way to identify certain symmetries and observables that are familiar in particle physics. For better or for worse, though, the details are close to, but not exactly the same as what we see in the standard model. Okay, so now that we have these Lie algebras and Jordan algebras in hand, we would like to go after the last two items in our wish list, namely, do the standard model representations fit into these octonionic purse blocks? And can we find a simple action that's going to make this happen? Well, in an attempt to keep things simple, a first guess at an action might look like this, where the B and the V are defined at the complexified level, and then we add a complex conjugate in order to have the output that lives in the real CL08 slice. So this is an interesting avenue to explore because it appears to be the simplest possible action. But it does not give us the particle content that we want, at least at known energies. And that is, it's going to give us the same structure that we see in supersymmetric theories, where we have an equal number of bosons to fermions. The standard model, though, as you may have noticed, has more fermionic degrees of freedom than it does bosonic degrees of freedom. So when we use this action, we don't get 3 linearly independent generations, but rather 2. And we end up instead with extra leptoquarks and Higgs bosons. So this action might be troubled from an experimental perspective, at least at the energies that we're interested in. Now, one might argue that this action is troubled as well from a perspective of aesthetics. That is, the octonions gave us the second pair of projection operators for free. And as you can see, this action is really only making use of one of those pairs, the little s projectors. So in order to, that is in order to separate out fermions and bosons. So said another way, we can see that there's a more refined Z2 grading here that, that our action can use so as to separate fermions and bosons. So in this case, we're going, if we obey this Z2 structure, then we're going to end up with more fermions and bosons, and perhaps, if we're lucky, even 3 linearly independent generations. Well, here is one such action on these off diagonals that will define fermions and bosons with respect to this more refined Z2 grading. Here are the projection operators P plus and P minus take into account this time the octonionic imaginary unit coming from both the left and the right. Now, in order to satisfy the fact that this is a real slice, we perform our action on a set of carefully chosen representative objects in the complex CL8, and then we add in the complex conjugate at the end, which ensures that we're living in the real CL08 slice. So now we're ready to answer the following questions. Do the particle representations of the standard model fit into these octonionic purse blocks? And using this action, do they transform in a way that is consistent with the particle physics that we know? Well, first, let's start with 3 generations of left-handed quarks. As a vector space, it so happens that they fit perfectly into these, into this subspace in green. Now, under this action, we find that these dark green blocks do indeed transform as left-handed quarks. Next, we find that left-handed leptons fit perfectly as vector spaces into this subspace. And furthermore, under our action, these light green blocks do transform as left-handed leptons. Finally, these 3 generations of right-handed quarks fits perfectly into these dark blue subspaces, and they transform as do right-handed quarks. So now we're at the point where we've covered almost all of the off-diagonal blocks, and the only fermions that we have left to embed are the right-handed leptons. And we find that this last off-diagonal block, last off-diagonal blocks do transform as right-handed leptons, but they only give us 1 generation, not 3. So we're missing an embedding for 2 generations of right-handed leptons. Okay, so let's leave those remaining fermions for now and move on to the bosons. Next, we find an object that is expected to eventually transform as a lepton's form momentum. This was not part of the standard model's particle content that we listed earlier, but it does appear within the momentum space representation of a standard model's covariant derivative, so it could be relevant for us. Now, in the next block, we find a similar form momentum for quarks, together with further representations transforming under the SU3 adjoint. So in the context of a gauge theory, these are expected to transform as do a full set of gluons. Now, in this bottom diagonal block, we have elements transforming under the SU2 left adjoint. And so in the context of a gauge theory, we would expect that these degrees of freedom to correspond to electro-weak gauge bosons. Although we in fact have too many of these representations here this time. So if we were to stop now, we see that we have 232 real degrees of freedom behaving in accordance with the standard model under the group SU3 cross SU2 cross U1 over Z6. So this is a majority of the 252 that we would need for the standard model if we were to include momentum operators and 3 generations of right-handed neutrinos. So when I say majority, I mean to say that we're at 92%. Furthermore, we can see some desired patterns emerge. In particular, we can notice that the bosonic objects like form momenta and gauge bosons live in the diagonal blocks colored here in orange. In fact, those extra form momentum blocks seem to be important because now the diagonal blocks appear to be describing a momentum space version of a covariant derivative. If we look at the off diagonal blocks, this is where the fermionic degrees of freedom are found. Now we're still missing 2 generations of right-handed leptons. Yet on the other hand, we seem to have too many elements transforming as do electro-weak bosons. So could there be a natural way to alleviate this tension? What I will point out is that these subspaces were based on one particular octonionic imaginary unit, as you'll remember, E7. However, if we finally introduce to this electro-weak sector another octonionic imaginary unit, orthogonal to the first, then it can act to further split this electro-weak block. The introduction of a second octonionic imaginary unit is something that we could anticipate because we expect this choice of octonionic imaginary unit to vary from point to point over what will be an emergent spacetime manifold. Oddly enough, when we do this, the diagonal block now provides us with a suitable space for these electro-weak gauge bosons. So now it fits the electro-weak gauge bosons perfectly. And the off diagonals now have exactly the right dimension to describe the missing 2 generations of right-handed leptons. So if we can get this electro-weak sector working in this way, we will then have covered 100% of the standard model's 3 generations of fermions and its gauge bosons. On the algebraic side, there would remain only 8 real degrees of freedom left in the algebra. An obvious possibility for these 8 degrees of freedom would be 2 Higgs fields, one corresponding to SU2 left and the other corresponding to SU2 right. However, it's too early to say more about this at this point. Okay. In summary, so in this talk, I ventured my current best guess to the question, what is the universe made of and how does it work? Hence, we set out to build a model based on the smallest number of initial inputs possible. This led to the proposal of doing away with the QFT picture of fields on top of a spacetime manifold. And instead, we propose a single structure of directed graphs. However, we quickly found that these directed graphs are not going to provide us with enough information to be able to explain why spacetime has 3+1 dimensions. So from this point, we propose that these directed graphs should originate from the operations of an algebra. Perhaps a clever choice of algebra could lead to an emergent spacetime that is 3 + 1 dimensional. With this in mind, we then started looking into the algebra of the complex quaternions. For one, the complex quaternions have a group of inner automorphisms given by SO31. Moreover, Conway knew back in the 1930s that most of the Lorentz representations that we now happen to use in the Standard Model can be described succinctly with this algebra. We then showed that the full set of Lorentz representations of the Standard Model can be completed by considering the discrete symmetries of the algebra. From these discrete symmetries, we found that actions of C cross H on itself, under which the Lorentz representations of the Standard Model appear as stable subspaces. These generalize the notion of an ideal. One might expect that such generalized ideals to emerge from the algebra, given that they survive no matter which element of the algebra is applied to them. Now, at this point, we emphasize that the internal degrees of freedom of the Standard Model had not yet been accounted for. So we propose extending C cross H so as to include the 4 finite dimensional norm division algebras over R, the Dixson algebra. However, this new RCHO algebra still has only 64 real dimensions, whereas the number of off-shell degrees of freedom in the Standard Model, including a separate Higgs and 3 sterile neutrinos, adds up to 244 real degrees of freedom. But nature then supplied us with a route out of this dilemma, namely that we can consider sequences of RCHO elements multiplying RCHO elements. The multiplication algebra gives us an incarnation of the complex Clifford algebra CL10. And curiously enough, the CL10 may be factorized into CL08 and complex CL2, which are the complex Clifford algebras familiar from real and complex Bott periodicity. If we're lucky, this might give us a route into something that John Bias and others call the tenfold way. Now, from this factorization, we proposed that we propose an algebraic starting point for what might emerge as a 3-dimensional space corresponding to CL30 and a Standard Model fiber corresponding to CL08. We then emphasize the perspective that CL08 is worth paying attention to because it is an unavoidable structure in the world of real Clifford algebras. We then pointed out how it may lead to a natural incarnation of a Fock space for Standard Model states. From here, we set out to concretely embed the Standard Model's off-shell degrees of freedom into a CL08 that is generated by the division algebras. We made use of a single octonionic imaginary unit to partition complex CL8 into blocks. And restricted within these diagonal blocks, we found Lie algebras and Jordan algebras corresponding to elements of a rudimentary covariant derivative. We furthermore restricted these algebras by forbidding quaternions to transform into octonions within the blocks. And then we took the real CL08 slice, and this left us with an SU3 plus U2 plus U2 Lie algebra and a corresponding Jordan algebra. Now, when acting on fermionic space, we find that these Lie algebras and Jordan algebras, they seem to come in these pairs. And this causes the fermions to exhibit what we call multiplet mirroring, namely an algebraic correspondence between 3 colors and 3 generations, between quark helicity and isospin left, between lepton helicity and isospin right. And then we then identified a relatively simple action that respects a Z2 grading with bosons on the diagonals and fermions on the off diagonals. And when restricting this action down to the Standard Model's Lie algebra, we found that 92% of expected states transforming under these symmetries in agreement with the Standard Model. We then pointed out that it may be possible to pick up the last 8% if the electro-weak sector breaks. Such a breaking might be affected by a second octonionic imaginary unit that is orthogonal to the first. There are 8 real degrees of freedom left over in this CL08. It may be possible to associate these with a left-handed Higgs and a right-handed Higgs. However, these details are beyond the scope of this talk. And that's all I have to say.
Okay, great. Thank you. I think that's a historic lecture. I'm glad it's been recorded. We will visit it again and again. Also because I think it has quite a few things which are not yet written down. So very exciting. Thanks so much, Cole.
Thanks.
Yeah, and can I just say, Cole, thank you for that. Was an absolutely surpassingly clear overview. I've rarely, if ever, heard such a wonderfully clear and at the same time, dense exposition of so much new material laid out so clearly. Thank you very much.
Well, thank you. I appreciate it.
So the talk is open for questions. Kindly use the raise hand feature. So as questions come in, Kon, I just wanted to mention, I think it's very good if you have two Higgs. It's like predicting one more Higgs, which I think is very good. I wouldn't be daunted by the fact that we are just seeing one right now and that you are predicting one too many. I think that's a good thing. So I hope we get that across to particle physicists. So Vatsalya, let me please unmute yourself.
Hi, it was a very nice talk. Thank you for the talk.
Thank you.
I have 3 questions. Like if you could go to the slide where you have the table of all the representations.
Okay. So let's say this.
Yes. Yeah.
Okay.
So here you have P mu, which is a space-time vector, and it does not transform under internal gauge symmetries. So is the interpretation that P mu provides us like vectors in space-time? So it emerges out of this representation?
That's a good question. So the only, I wasn't dealing at all with space-time symmetries yet at this point. So the only symmetries that I was analyzing this under was the SU3 cross SU2 cross U1 symmetry, so the gauge symmetries. And so under that, then these are just singlets. And so that's consistent with what we would expect. It will be another step in order to get space-time symmetries into this model, and I expect it to be non-trivial.
Another question I have is, like, from this model, it seems that the 3 generations of fermions, they are absolutely identical. Is there any way to differentiate between them? Because we know that one generation is much more stable than the other 2.
That's again, a really good question. So actually, this is one of the things that that I like about this model is that the 3 generations are not showing up as identical. So the left-handed ones are, so this is also something that so this is a good point that you're making. It would be nice if in our particle models that somehow the 3 generations come up, they emerge as being algebraically different from each other, so that they can have different properties. In this model, the 3 generations do come up as different from each other. They're kind of scattered over the off diagonals. The only symmetry there are here between the 3 generations are the left-handed ones. They seem to be exact copies of each other, but the right-handed ones, they're kind of dispersed in different places in the off diagonals. So if there is a difference, I would expect it to come from that.
Thank you.
And you had a third question.
We go, John, please go ahead.
Hi, Cole. Thanks very much. Do I understand you, from somebody fairly new to this, do I understand that you're suggesting the imaginary units in the octonions are somehow Higgs fields? And if that's the right picture, how does that relate to the Higgs that we know already? Or is that?
Can you? I didn't hear the beginning of your question. Can you repeat it?
Yeah. So I think you're suggesting that these imaginary units in the octonions are somehow Higgs fields. Is that what you're suggesting? And if so, how do they relate to the Higgs that we already know about?
Right. So I wouldn't say that the way that they're appearing here is as the octonionic imaginary units. So the octonionic imaginary units gave us these blocks, but I wouldn't have identified classified it as the Higgs. The way that so if this is still to be worked out, because the electro-weak part is the part that is still needs some steps in order to be completed. But the way that it's looking right now, the extra degrees of freedom that are not yet accounted for actually live in the SU2 left adjoint and the SU2 right adjoint. So if they were to be Higgs, they wouldn't be, at least at first sight, they don't look like they would be the same as the Higgs that we have in the standard model. It's just a different representation. They would have to be. I'm not exactly sure how this should work out yet. I think in order to get the electro-weak part to kind of break in the way that I would like it to, I think this we need to really move beyond just looking at the representations of this algebra, and rather like actually turn this into a gauge theory and have this this octonionic E7 vary from point to point and see what happens.
Okay, thanks.
Okay.
Thank you. Thank you. Davian, please unmute yourself. Go ahead.
So I just want to follow up on your answer there, Cole. Did I hear you say that your extra degrees of freedom correspond to 2 adjoint SU2s?
That's what that's what it looks like at first sight. But of course, I can see already that there's going to be more. Like once this is built as a gauge theory, there's going to be more details about how this these electro-weak bosons are going to kind of break, kind of emerge from these bottom blocks.
And again, just following up, are those the only adjoint degrees of freedom that are showing up here?
Well, there's gluons in the a couple things to say, but there's gluons in the top blocks that are the adjoint under SU3. So the gluons are in there, and there's and the electro-weak bosons in the bottom block. One thing I should mention is that it looks like there's that the electro-weak are kind of entirely in the bottom block, and the gluons are in the top half space. But actually, when you take the real slice, there's a symmetrization that happens, and they kind of end up being spread over both. So this looks like it's asymmetric across that axis, but actually it's not as asymmetric and as ad hoc as it might look at first sight.
Okay, thank you for that clarification.
Yeah, no problem.
Great. David, go ahead, please.
Well, thanks for the excellent talk. So I just had a question about potentially getting a graviton in the C cross H cross O model. So as we know, a spin 2 graviton would be a tensor product of 2 vectors. So I was curious, do you think when we take that tensor product and we're working with C cross H, would it be a tensor product over complex numbers such that we get C cross H cross H? That was just an idea I had when I was looking at this a while ago, but I didn't finish looking into it. I was just curious if you had any thoughts.
That's also a good question. So this is something that I'm just starting to look into, and there's different ways to go about this project. And the first way or one of the ways that we've spent a lot of time looking at it was you start with the complex CL8, and there's kind of 2 obvious routes. You can go the CL08 route, which I like because of because of its connection to Bott periodicity. But then there's also a Jordan algebraic route where you look at the Hermitian real slice, which is a different real slice. Now, in that kind of line of thinking, there's actually a really natural way, or what looks to me like it could be a natural way to build a Vierbein, and then actually that this whole thing might be interpreted as a generalized Vierbein. And so you might be able to just kind of build everything off of that. So that's actually what looks to me to be kind of like the easiest route to try to bring gravity in. This Bott period, this other real slice that I'm presenting today is new to me. And so I haven't thought about it long enough about how exactly to bring gravity in, except for the fact that you can notice that the complex CL2 might be reinterpreted as a CL30, and maybe this could give space sometime, but somehow, but it's not as obvious to me in this case, like how you would go about bringing gravity in.
Can I respond to that, Cole? You seem to be having an extra SU2, if I understood you correctly.
The SU2, right? You mean?
For me, that's gravity, actually, you know. You have SU2L and SU2R. This is what we have been elaborating in our papers. I mean, your gravity sort of hiding in plain sight because
will it affect all particles? Like, will it act on like gauge bosons, for example, or like will you?
The thing is that so I have essentially something like 2 copies of CL8, which is CL9 thought of as a direct sum of 2 copies of CL8. One that corresponds to left-handed chiral fermions, the other to the right-handed chiral fermions. The 2 Higgs, I have 2 Higgs like you have. The standard model Higgs is giving mass to the left-handed particles. The second Higgs is essentially giving electric charge to the right-handed particles. So gravity has a symmetric role. Of course, I come with extras. I don't just get general relativity. I have a mirror copy of the standard models, SU2, SU3 color cross SU2L cross U1 electromagnetic or hypercharge has a copy SU3 grav cross SU2R, which is general relativity, and a U cross a U1 grav.
Does the Higgs end up coupling left-handed particles to right-handed particles in your model?
Yes.
Okay.
That's why it's important to have the second Higgs. And it seems in several ways that the extras that you are seeing, which we are trying to accommodate, would fit in nicely if already at this stage we start taking care of gravity along with the standard model instead of leaving that for later. So my naive guess is that you're almost there, but to exactly get from 92% to 100%, now is the time to, bring in gravity right away, and that is where things seem to start falling into place. And so that's why I wanted to ask you, have you looked at having 2 copies of CL8? That would give me 512. For me, that's good because very close to E8 cross E8, 496. And,
but then don't you then have a doubling of the number of degrees of freedom?
I have, you're saying I have too many? No, once CL8 go for the left-handed particles, which are singlets of SU2R, the other CL8 for right-handed particles, which are singlets of SU2L. The gravity is the right-handed counterpart of the weak force. Somehow that comes in very strongly.
Yes, I haven't thought about using the SU2 rate for gravity.
If you remember Peter Voigt's paper on Euclidean twistor quantization, he says the same thing that, SU2R is adequate for constructing general relativity.
Oh, he did have something. He was also using Ashtekar.
Yes. I'm saying the same thing, except that is Euclidean, and that's something we have to worry about, Euclidean versus Lorentzian, but we can come to that. I don't think that's necessarily insurmountable. But, when you break the electro-weak sector, for me, the counterpart of the electro-weak sector is SU2R cross what I call another U1, which I call U1 grav. So there are additional predictions, but I wouldn't say they are not there. Maybe we have to think what is SU3 grav doing. U1 grav is very much behaving like MOND. So for me, there's no mysterious dark matter. It is really modified the Newtonian dynamics on larger galactic scales, and somehow that seems to go well. I think hands are up. I should. Jens, please unmute yourself. Thanks, Cole. Thanks for the response.
Yeah. No, my pleasure.
Hey, yeah. So yeah, thanks. Great talk. Thanks for the rundown and everything. So cool. So I have to follow up on that. Breaking the electro-weak sector with an additional octonionic phase. That's cool. Just a very quick remark at the very beginning. You mentioned the current investigation in that field, and I'll just add, and maybe you said it, that Gursey and Gunayrdin also worked on the exceptional Jordan algebra for this kind of things. And I mean, it's contained in at least one or two of those references that you had. And but again, yeah, it points again back all the way into the 1970s. So they've been working on that cool stuff.
Were
already.
was it a 3-generation project that they were working on?
I would have to dig up the details, and I'm actually curious about digging up the details. They didn't just do the exceptional Jordan algebras; they also did other variations of on top of Jordan algebra. So anyway, but next to their SU3, algebraic strong force. Anyway, just wanted to add that there, and they also use Pierce decomposition then on the exceptional Jordan algebra to isolate where they think, but I mean, it's just amazing.
I imagine it probably was it probably was a 3. I imagine it probably was a 3-generation effort, because if you've got the exceptional Jordan algebra, why wouldn't you go for 3 generations?
Yeah. It can't have been the.
I haven't seen those papers, but I'd be curious to see them.
I'll find it.
I think you're the person actually that you were the person that introduced me to Gunayrdin and Gursey in the first place anyway. So
yeah, that was cool. 13 years ago.
They owe you. You're their best advocate.
No, Jeffrey is on the call here too, so don't forget him.
I said you're their best advocate. I said that you advocate for them.
Yeah, sure.
Thank you. David Jackson, please go ahead.
Hi, thanks Tejinder, and thanks Carl very much for the talk. I liked very much the talk and the introduction particularly. So you mentioned going beyond space-time, and you went via directed graphs, and then that originating from algebras and then motivating a particular algebra leading to the standard model. I lost track of where the directed graphs come in. Was that just a kind of a stepping stone, or how does it connect? I mean, I don't know anything about graph theory, but does that do with building the space-time, or where does the directed graph kind of come into it? Well, why not just go straight to the algebra?
Oh, I see. Well, the original idea was basically to take something that looks like a Feynman, like sum over paths, but like a discretized version of that, just as something that could be. It started out just as like literally as a game, as like what's the simplest possible thing you could imagine that could still capture some things that we see in nature, and so that's where the directed graphs idea came from. And then from there, I don't see an obvious way to explain why there's 3 + 1 dimensions. So making these things algebraic was a way that maybe if the say for example propagation along an edge could be given by multiplication by the algebra, and so that would give you a directed edge, and then for example like joining of 2 edges at a vertex could be given by addition. So there could the graphs could kind of correspond to operations in an algebra. That's just one way that it might kind of materialize, but
okay, I need to think about that. Yeah. So in terms of going beyond space-time, where does the kind of extended space-time, how is that get constructed? I mean,
how do you get space-time out of this?
Yes.
Yeah, that's a good question. So I'm not, so yeah, I guess. So one thing is that these things will naturally be Lorentz representations. So you kind of already have part of what you need. I wouldn't necessarily go as far as Poincaré because I don't want to kind of assume like a whole manifold. But kind of building a model, like actually building up a model and getting the kind of gravity aspects of it, to me seemed like the hardest part. So that's what I figured would be best to do last. The thing that seemed like the most straightforward, in order to kind of tackle this, you have to start somewhere. And the idea was to find, like, do the easiest problems first, learn what you can from those parts, and then use what you learn from that to kind of inform yourself on what to do with the more difficult parts of the problem, like getting an emergent spacetime or describing gravity. And so the thing that seemed to me to be the most obvious, well-defined question to try to answer is, can you find an algebra where you reproduce the representations that we find in the standard model by just having this algebra act on itself? And that's, been a project that's obviously taken, been working on that aspect of it for a long time now. But I'm now at the point where, I need to start actually thinking of this now as a gauge theory, and then seeing kind of what can be done if it's possible to incorporate gravity. But this is, something that I'm just at the point of starting to do now.
Sure, great. Okay, that helps a lot. Yeah, thanks very much, Cole. Thank you.
My pleasure.
Thank you. So if I would like to respond to both David Jackson and to Cole, because it's a very interesting point. The time now to bring in space-time. The way I landed up with the octonions was because I was concerned with this question that quantum theory depends on classical space-time, and that is not good except as an approximation, because the quantum superposition principle disallows the point structure of space-time that we take for granted in R4, even in quantum theory at low energies. So that is when I realized that one of the ways to get over this commutative space-time is to look at beyond real numbers, the division algebras, which have non-commutativity already built in, the quaternions and the octonions. And there's a very important hint coming from the quaternions when we look at the Dirac equation. So it's worth asking, what are these gamma matrices doing? They look very mysterious. To describe fermions in 4D Minkowski spacetime, I cannot use Klein-Gordon. I must use the Dirac equation. Then I realized, I learned from Athiya in one of his lectures, he said that the Dirac equation was actually first discovered by Hamilton, not by Dirac. Why? Because if you take a quaternionic space labeled by the 4 quaternionic directions, the gradient operator on this space is actually the Dirac operator. So when we put in gamma matrices into the Dirac operator, we are actually trading them in for quaternionic space. So my electron doesn't even live in a Minkowski space-time. It lives in a quaternionic space, and that's already a big hint. And as you rightly said, the quaternions and the accompanying SL2C are not big enough to accommodate color in the quarks. So we do the next best thing. Instead of considering the gradient operator on the quaternionic space, I consider the gradient operator in an octonionic space. That just turns out to be the Dirac equation in 10D space-time. No, in the quaternionic case, okay, it's 4 and 4, or maybe 4 and 6. And when you go to the octonions, it is 10-dimensional space-time. So because I need to remove the R4 space-time manifold from quantum theory, I want to replace it by a non-commutative manifold whose coordinates, so to say, are labeled by the octonions. That is my way of looking at why octonions are so important. They're important for quantum theory. And because they label space-time coordinates, the curvature of that space-time is indeed gravity as well as the standard model fiber. As you talked of, you have a fiber cross for SL2C structure that's already there in the octonionic space. And the way space-time, to answer David Jackson's question, how does space-time emerge from this? In quantum theory, there is no space-time. There's just this octonionic space. When I take the classical limit, actually quantum to classical limit as in quantum theory, then there's a certain averaging process which converts quaternions to Minkowski space-time and octonions to Minkowski space-time cross the fiber on which the standard model gauge fields live. I wanted to use this opportunity to give my picture of why I landed up with octonions and what do they have to do with space-time. So if you could get gravity in at this stage, I think we are done already.
It's easier said than done, I think. Maybe it's easy for you.
No, it's not easy, but I learned from you. I mean, I used your CL6 for one generation. And then, but by the way, I wanted to ask you, when you said a second imaginary octonionic unit, orthogonal to the first one, are you not already going to split by octonions?
Split by octonions.
CL7, the CL7 algebra. CL3 is split by quaternions, CL2 plus CL2. CL7 is CL6 plus CL6. And that's algebra of, no, like, you know, like in your video lectures.
I don't think I'm using a second, I'm not using a second copy, like a second copy of the space. It's more that, so it's kind of, you know, a similar idea that we see in gauge theories where things vary from point to point. And so this frame, like, so if you see this picture on my screen here where I've got the blocks, they're all defined by a single octonionic imaginary unit, but you would expect that along the graph or along what becomes like an emergent spacetime that that E7 is allowed to vary from point to point. And so just as, you know, things vary in gauge theories, this kind of whole frame is allowed to vary. And then you end up with these breaking of the blocks when basically something with one frame kind of makes contact with another object that is has got a frame of based on a different imaginary unit than you might expect to have these things. But it's,
why don't you work with the split by octonions? Why I emphasize that, you know, here we have a puzzle here. Why is the standard model, you know, left-handed? Why is it singlet under the right-handed fermions? The answer to that is because it is, if you extend to include gravity, you get gravity is the doublet under right-handed fermions and a singlet for left-handed fermions. And the bioctonions very naturally have that structure. CL7 and CL3 being the only two Clifford algebras which have two irreps, these two pinners, and they are parity reversing. Yeah, think of CL7 as two copies of CL6, a direct sum, one copy for the left-handed fermions, one for the right-handed fermions, and things seem to work.
Why would they have? Why would one have an SU2 symmetry and the other one not? But I guess you're saying that the SU2 symmetry for right is you're interpreting as gravity.
Yes.
Okay.
Yes.
So is this so just a question? So in your models, like, do you have one picture that is it all part of one big coherent picture, or do you have kind of different models?
No, I think in this latest paper, when we try to derive the CKM matrix, we feel we are beginning to reach a coherent picture. So I'm somewhat closer to CL9 than CL10 right now. CL9, I think of as two copies of CL8. The first copy our branch is Cl6 cross Cl2. The second copy also has Cl6 cross Cl2. And yeah, something else very puzzling has opened up from here, that so with one Cl2 I associate weak isospin, the other Cl2 with the Lorentz space and then gravity. It seems as if the weak isospin is coming with its own copy of a 4D space-time. So it's like as if there's a Cl3 giving us 6D space-time before a left-right symmetry breaking. And the left-right symmetry breaking is giving me two copies of 4D space-time. It seemed to be different, as if just as gravity is the curvature of our 4D space-time, the weak force is the geometry of the other 4D space-time. So weak force is looking more like a space-time symmetry than internal.
Do you see any reason why so like with the internal symmetries we end up with unitary symmetries, whereas the space-time symmetries are not? Do you find any explanation as to why?
Is it like why gravity should be SU2R? Why should it be a gauge theory?
No, just like with the this is something that keeps me up at night, is like, why do internal symmetries we get these unitary symmetries, whereas space-time symmetries will be, like Lorentz group, or like they're from a purely algebraic point of view.
Okay, my picture for that is, if you know that I talk of these so-called atoms of space-time matter, where the one space-time matter atom is the fermion along with all the bosonic degrees of freedom. So there is one copy of this non-commutative space-time, this larger space-time which contains internal symmetries for every so-called space-time matter atom. And classical space-time has to be constructed after symmetry breaking. Now, I don't have a classical space-time with this Lorentzian classical structure before symmetry breaking. So before symmetry breaking, gravity truly looks like a gauge theory with, like a SU2R, which might answer your question. Later on, it starts looking different in the emergent classical limit. But before symmetry breaking, gravity is really truly like a Yang-Mills, or you can call it pre-gravitation. I don't know if I'm answering you, but maybe you can bring. I think David has a comment. David, can you please say it out? David? Yeah, go ahead. Please unmute yourself.
Hey, you just comment on what I was saying about CL8. Yeah, I mean, right. So CL8 does have 256 dimensions, and E8 has 248. So it's natural to ask the question, oh, does E8 fit in CL8? But algebraically, it does not. But I believe Duchamp has done some work that looks at connecting the Gaussian polytope, which is the E8 root polytope, to CL8. I mean, maybe one point is that the E8 root lattice is in 8 dimensions. So yeah, I was just mentioning that.
Yeah, since the audio is not very clear, David, I'll just read out your comment. David says, I believe CL8 is connected more to the Gaussian polytope in the E8 lattice than the E8 Lie algebra itself. So perhaps looking into Deschamps' work in relation to CL8 and the roots of the E8 polytope could help find connections between Cole's story on CL8 and arbitrary models using E8 in some way. Okay, thank you. I keep this in mind. I need to understand what's being said here. Maybe I could ask you, Cole, where do you see E8 fitting in your story, and also the exceptional Jordan algebra? I mean, does it have some connection with CL8 in some way?
That's a good question. That's a good question for both of them. It's not something that I've spent a huge amount of time on with either of them. I've got a long list of projects that I would like to work on, and they are included in that list, but they're not something that I've ever kind of come around to doing. But I've got kind of ideas for both that I would love to kind of explore, but at this point I don't have a lot to say because I haven't spent a lot of time on them.
Thank you. So I
think the general question of like knowing what mathematical structure to choose is a really difficult one. No matter which mathematical structure you choose, you have to ask, like, why would nature have chosen this thing over something else? And
yeah, but you know, the way I like to come to
like I like to try to like pick ubiquitous structures, like things that are kind of unavoidable somehow. And that's why I like the division algebras, is that they're kind of everywhere. And that's also the motivation behind this Bott periodicity stuff, is that they're kind of everywhere. They're unavoidable.
Very interesting. Fock space from Bott periodicity. I think it's a really nice idea. I definitely hadn't thought of it. I think it would be very useful. So regarding what you said, about picking up which mathematical structure to choose, for me, what's more important is the physics question that I'm asking. That comes first, and then I go looking for a structure. So in that context, I wanted to mention, how I got interested in this mass quantization question, is to note that the mass ratios of the first generation down quark, up quark, and the electron, the mass ratios are 9:4:1, and the square root of masses are in the ratio 3:2:1, whereas the electric charge ratios are 1:2:3. For me, this is very striking. So motivated by your result that there is charge quantization, I introduced for the right-handed sector, the second CL8, there is again a U1 quantum number, but for the right-handed particles, my U1 charge is not electric charge, it is square root of mass. So I interchange the location of the down quark and the electron. The down quark becomes a singlet under SU3 grav, which is with the right-handed sector. The electron is now a triplet under SU3 grav, but it is very useful to get in this U1 charge, which is square root of mass, because someday I need to explain why the down, up, and the electron have square root mass ratios of 3:2:1. It's telling us something. I mean, if you found charge quantization your way, I would definitely do the next thing, and hence conclude that mass quantization is also from a U1 number. And then, interestingly, the U1, right-handed U1 square root mass number is the same for all three generations to begin with. The reason the mass ratios look different is because we make all our measurements using electric charge eigenstates. When those mass eigenstates are written as superposition of electric charge eigenstates, the masses start to look funny. And even then, the first generation mass ratio always remains simple. So I say this because I think you have almost all the same kind of structures, I realize, after listening to your talk. And I think I would seriously considering bringing square root mass in right away as another U1 charge, analogous to electric charge.
Okay, so the thing that you're claiming is that there's there's four, is it neutrino, electron, or I guess it's a electron down quarks and up quarks, and it's the mass ratios of those.
So in my right-handed sector, there are three sterile neutrinos. one sterile neutrino, right-handed sterile neutrino, is the idempotent on which I build the right chiral fermions. And the first excitation is now not the down quark. It is the electron, which is a SU3 grav triplet. Next comes the up quark, same as in your classification. And the singlet is now the down quark. The down quark and the sterile neutrino are singlets of SU3 grav, whereas the electron and the right-handed electron and the right-handed up quark are triplets of SU3 grav.
Okay, so the claim I was asking is, so the claim is that that is the mass ratios for all four of those types of particles for the first generation, is that right?
They're good, yeah. So well, the neutrino as of now seems to me to be massless. The reason for neutrino flavor oscillation is something other than mass that we can argue separately. So the square root mass ratios for the sterile neutrino, for the electron, for the up quark and the down quark are now 0, 1/3, 2/3, 1. It's the same pattern as you have for the electric charge, but I deliberately switch the position of the electron and the down quark.
Okay, I haven't seen it yet, but I still do have to look at it.
Yeah, thank you. David, you want to say something more? C cross, O cross, O are curious. Yeah, I use C cross O as this complex split by octonions. Okay, please, we still have time, another 10 minutes. If you have any comments. We have a participant, Hilary C. Could you kindly, I thought what you're saying looked very interesting. Could you kindly come up and say what you're saying?
I'm not sure it's actually as interesting as you seem to think it is. I just speculated that maybe there are two Higgs, but if we can't tell them apart, we would be none the wiser.
Yeah, but
these would have two different, one would be would transform under SU2 left and the other one under SU2 right.
Okay.
They would be different. Yeah.
And by the way, for me, one of the Higgs is charged. Well, the new Higgs, the non-standard model Higgs, is actually electrically charged. I think particle physicists have to say something about it.
Right, because I was wondering, you can have something that in terms of the structure is a different, separate thing, but if there's no procedure or measurement that you could define, that you could do in an accelerator that would allow you to tell them apart, then it wouldn't show up in the data. But from what people are saying, this would be detectable if you got left versus right, or, if it's charged, it would stick out like a sore thumb, surely. Unless it's very, very massive, I suppose, but Higgs is heavy. Maybe the other one is even heavier. I don't know. I'm a quantum information theorist, okay? So
one other useful lesson that I saw in this algebra studies, for me at least, the Higgs is composite, most certainly so. It seems to be made of the very fermions to which it is supposed to give masses. Cole, have you seen something like compositeness of the Higgs?
Yeah, I know that there's composite Higgs models out there, but yeah, again, it's not something I've spent a lot of time on, different Higgs models. Jens has a question.
Is there a hand up? Yes, Jens, please. Let me, please unmute yourself here.
Okay. Emma, can you hear me? Yeah. Just want to quickly, so with mass, and so in conventional physics today, we think of energy momentum properties as quadratic forms or quadratic types to be conserved between equivalent frames of reference. So when you talk about square roots of mass, so does that mean that you're looking at fourth order conserved properties between equivalent frames of reference?
Seems so, yes. Also, interestingly, the square root of mass comes with both signs. Mass is positive, but when I take the square root, it has plus minus square root m. And my understanding is that's how I would define matter versus antimatter. Matter has square root m positive, antimatter has square root m negative. It was always puzzling for me that when I call something as matter particles, it has positively charged particles like the the down quark and the up quark, and it has negatively charged particles like the electron. So clearly the sign of the electric charge is not a dynamical variable which discriminates matter from antimatter.
Sure.
Whereas the
So,
sign of square root mass very nicely, tells me. So, right.
Yeah, so I'm certainly sympathetic to exploring in that direction. I just want to point out that today a lot of people find spinors useful for the description of nature, and they require only quadratic conserved properties.
Yeah,
so if you're saying that we have to look at something other than spinors for fundamental particles, that's a big ask.
Well, there are two ways of looking at it. Firstly, the square root of mass, the little I know about supersymmetry makes way, it comes there too, right? Because the square of the supersymmetry operator is what gives you the space-time operator or the Dirac operator. So already, in some sense, there's a hint of a square root mass there. And and the way, to my understanding, say Cole makes spinors is the octonionic algebra acts on itself. So again, I would think that, a quadratic or bilinear in the octonions, if you want to make a spinor, and if I associate mass with the Dirac spinor, I have to then talk of square root mass at the octonion level. Square root m into root m to get an m for the spinor. That's how I am inclined to.
Yeah. So the way I understood it, when you pointed out this here, the real CO2 for gravity, you are understanding it in this sense, and then I think as mathematical implementation, not spinors anymore, but fourth order conserved properties. And conversely, if you want to stay with spinors, then I think Cole's concern is like, well, what does this real CO2 do like everything else in your representation?
Look at this very interesting thing that the Klein-Gordon equation is quadratic in mass m squared, but the source term for Einstein equation is linear in the mass. It's very striking, right? The energy momentum tensor is not m squared, it's m. And that again seems to tie up with, that it's like taking an underlying theory with square root m, squaring it, and then arriving at gravity. Maybe.
Yeah. You don't have to convince me about this path at all. So yeah, thank you. I appreciate you talking about it.
Thank you. I think David, I'll read out his comment. Krasnov and a collaborator looked at obtaining fermionic Lagrangians from Klein-Gordon with a first order constraint. The fields obtained there seem to be a field redefinition from standard ones by square root m. Okay, thanks. You're using not sure. I'll try to see this paper long ago, 2012, yeah. Thank you. Cole, you would like to add something? You could finish in time. That was nice, yes.
Oh, yeah, just barely. I think it was only 5 minutes over, so it was not nearly as bad as I expected. No, I just wanted to say thank you to everybody for showing up and, for your questions. This has so far been a really friendly conference. And
so how do you make contact with quantum field theory? I mean, if you want to work with octonions and quantum field theory, how would you go about it?
That's a good question, because I, would really like to start from this, from this really rudimentary picture of algebraic operations, and to kind of come up with something that resembles quantum field theory in a limit is obviously not trivial. But I do have ideas for, there's a lot of things that kind of need to be constructed when you're starting with such basic objects. And yeah, I certainly do have ideas about that. But again, this is kind of right at the point. This is kind of where I'm at in my research right now, is to start to.
Yeah, so maybe I take this opportunity to ask Professor Steve Adler, if you are there, Steve. I had a question for you. Steve, are you there? I think Steve's not there yet, because he has looked a lot at quaternionic quantum mechanics. He has a book on it. So I wanted to ask what he thought of the extension to octonions, but I think I'm not sure he's there right now.
Yeah, yeah. David also made a comment in the chat, and just about a paper that me and I wrote for one generation that you. So there is a connection there to QFT. So it's possible, like it is possible. There's kind of an obvious thing that we can do, which is that the octonions, or like the division algebras acting on themselves are going to give you group representations, and so you can build a QFT and just use that algebraic structure to replace the representations that we use in the standard model. So that's certainly something that can be done. But
yeah, so I think you
kind of like on a bigger level, like what I'd really love to do is start from something really super simple, and then
because
kind of
earlier on in your talk, you referred to this sociological pushback against division algebras. I think part of the resistance, which I also was told, is what can you calculate for quantum field theory? Like, can you, for example, tell what's the G -2 of the muon? Do you get a result different from the standard model? So those kind of questions. Maybe the reason that is we are not doing dynamics yet. We are still looking at the algebraic structure of the standard model. But if they are interested in questions like, calculate something like QFT does.
Sure, if there is some prediction, if there's some prediction that made, even if you could, there'd be a couple ways to go about it. Yeah, there's a lot to say about that, kind of what's sociological, and but yeah, if somebody had a huge breakthrough, where they predicted something that is not known from the standard model, then that that would certainly change the story, wouldn't it?
That's where I would push for calculating values of the fundamental constants. That's one thing they cannot do, and one thing which we may have opportunity for, in my opinion. So yes, Michael.
Yes, thanks very much, Tajendra. I really hesitate to put this question because I have such no background in particle physics at all. And the only thing I can bring to the table is a general interest in particularly the framework of Bott periodicity from the framework really for kind of purely mathematical study of Clifford algebras. But on this certainly very fundamental question of how one brings in some notion of an emergent space-time structure, which also, clearly goes to this criticism that has been made by some of the people pushing back that at the moment as it were, so far the program has really only addressed the algebraic structure of the standard model, hasn't, as it were, gone into issues about dynamics, and clearly one would have to go into those issues about dynamics in any development which did bring in space-time algebras, the space-time